it's going to be, if you miss a lecture, you can go watch it. So there's an advantage to it. And also, the stuff that we do is all available on the web. The paper that you see before you is just a old-fashioned, but it really does help to have something to take notes on. It's hard to write on your computer screen something to look up later, right? Or to ask questions about. And so the textbook is designed so that you're always facing a white page for each page. So you can make notes up in the upper portion there where it's white, right next to the page that you're reading, and have some question about. Today we're going to do a lot, and I figured why wait. And, we're just going to go right through the logic of the simplest beginning of classical mechanics that I have been able to think about. And that is just to have two particles run into each other and make a geometrical story of that, being very careful to use the least number of axioms. In other words, logical efficiency is the real modus operandi for this whole course. But we're going to make use of it right at the very beginning here. And the constructions that we'll do will mirror that logic. So let's, as you can see on the second page here, there's a tragedy going on in this story right here. Two cars, one of them an SUV. Now I've got to make sure that everybody knows what an SUV is. How many people know what an SUV is? I just want to, you know. Bill, I think, knows sports utility vehicle, right? Also, a gas guzzler, right? They're usually very inefficient. And this particular one is driven by a real idiot who's busy running his cell phone and faxing or something. And here is the liberal of this story in a little VW. Now VW, that you know what VW, Volkswagen, okay, Volkscar, right, from Germany, right? World War II, okay. Now it's a very popular car. Anyway, this person is probably had too much grass and is going very slowly, 10 miles an hour on freeway. It's not a good idea to do that, right? Especially if you got this guy, okay, going 60 miles an hour. That's 1 mile in a minute, okay? So those are the classic English units. And this is just a countdown to the collision. 90, 48 seconds, 36, 24, 12, minus 6, and so on. So this is one way to portray the beginning of a collision. And then what we're going to study is the mathematics. And it's neat because this takes us right through Lagrangian and Hamiltonian mechanics, and the geometry and algebra of that is derived by just looking at these two things coming together. That's what I'm very proud of for making for this course. Two cases. One is called kabong, and that's something that might happen in a parking lot, not at 60 mile an hour speeds, but I'm going to have you work a homework problem at very low speeds, assuming what we call a perfectly elastic case. And how perfectly is, we'll discuss that later on. And then this is the other extreme, a totally inelastic case in which they just crunch together and become one piece, one particle, one mess, one mass. Okay, so that's what we're going to talk about today. We're going to analyze that algebraically, geometrically, and we're going to begin the learning about tensor and quadratic forms while we do that. Okay. So, what we, of course, have always in the background, the usual way of handling a problem like this. Okay, so the way I say it is you look up the usual momentum and energy formulas. And what I'm saying here is we're going to see if we can solve this easily with, first of all, just one, or really 1.5 axioms. Okay, so instead of doing that, we're going to derive what energy is in a better way of understanding. So we're going to have just really one axiom for this whole story, but there's a sort of a half axiom that is always hidden in classical and quantum mechanics in order to make it, both of them work. So we're going to ask that these two masses together keep the same total momentum. Now, this guy here has a mass of 4 tons. This is how he has a mass of 1 ton. Okay, so it's a 4-to-1 ratio. It's pretty scary for the poor Volkswagen to have this all happen, but we'll talk about that. So this is a very unconventional, this whole course is unconventional, but we're going to keep coming back and seeing the conventional ways as we go. But to solve this problem, we really only have to draw 2 lines. So it's really simple. Okay? So rather than just quoting these formulas, we're going to derive them, basically. We're going to make sense out of them. Okay? So the idea is that during the collision, which at 60 miles an hour is very short, boom, or kabong if the cars were really made out of some sort of super elastic material, but most likely it's a crunch. Okay, in which very violently we change the velocities of these two objects. The idea is this axiom. This axiom says that even that violent collision happens so quickly, this quantity here is not changing. That's our axiom. And that's the axiom of classical mechanics. All of the stuff that we're going to get for this whole course come from that. Now, quantum mechanics, I'm going to keep talking about how you do it in quantum mechanics. The stuff that's going to be on the board here just for this course, it's left over from last year, is when we do quantum mechanics, I put 2 beams of light colliding with each other and make all of it. So their energy is the thing that comes first, frequency actually. But that's getting ahead of the story here. Now, Unit 8 of this text takes that up. So we're going to do a little bit of that at the end of the course. But for the time being, we're using Occam's razor. That's the idea of being very careful of our efficiency, a logical efficiency. And here's Occam's idea. This is it in Latin. As a number of interpretations. Literally, don't make pluralities. Pluralities, no, don't make them. Or conjectures without necessity. In other words, make sure that you're careful about the beginnings of whatever it is you're doing. And logically, it's just assume less to prove more. Or if you're doing coding, if you're making your program to do the stuff that we're going to do in this class, keep it simple, make it powerful. That's a very important idea. I mean, this guy's 1300s, right? You already realize that this is an important idea. Now, this is a Western idea. In the East, things like this were happening too, but they were more compartmentalized. This guy traveled all over the world. He walked all over the Western Hemisphere, from monastery to monastery, learning as much as he could, and talking and arguing with people. So, basic idea is that the input values of the velocities, which are 60 miles an hour and 10 miles an hour here, okay, are going to sum up with the mass coefficients, mv, to the same numerical value. This is going to be a constant after the collision, however violent and short it is. Okay, so basically we're asking what is the final velocities given that I have a 60 and a 10 here. Okay, so this is the algebra basically, and that results in a very simple algebraic equation But how do you handle that? How do you make a map of that equation? And this is a hard way to look at it. Looking in space and time, or looking in space and space, is not the best way, perhaps, to do this. So what we do is we draw a graph, and that's what we're going to do now with the graph paper. Okay? Is we're going to put the axiom on that graph paper. First of all, we have to identify the end point, the initial point. So we said we're going with a, now label the axis here, the graph paper that I gave you that has 10, 20, 30, 40 along it. That's what we'll use, so let's get that out. I should have one right here. It's the one that looks like this with a 10, 20, 30, 40 and all that. So we could do lots of collisions on this piece here. The graph that, all the part of the graph that you need is this part right here, positive velocities for this particular case. So here on this axis is VW. So this is velocity of Mr. VW, okay, velocity. And this is in miles per hour, just using a good old-fashioned English kind of units that are used by traffic cops when they give you tickets for speeding. If you've ever gotten one of those horrible things. Anyway, and down here is the SUV velocity. So these are in miles per hour, mph, both axes. And here, right here, is the 10 miles per hour for the VWs puffing along there. And here comes this SUV. It's roaring along here at 60. Okay? So our initial velocity is right here. 10 and 60 coordinates. Okay? Now, the equation that we've been writing here is a very simple one. It's just an equation of a line. And there's the whole picture right there. I'll put it up on the screen. It's easier to see. And what you'll notice is that this line has a nice slope to it. It's a negative slope. Okay? And that, in fact, it's a negative slope with the mass ratio, MSUV over MVW. Okay? So it's a, this is the velocity and the x-axis, the horizontal axis, and this is the velocity on the vertical axis. So this is an equation that's sort of written here. In this form, it would be y or minus 4x equals, well, whatever this thing comes out to be. That's the initial values. But we just put the initial values out without working out exactly what the momentum or energy of that is. We'll figure that out later. But we do know that as the SUV crunches into the VW is going to gain velocity more quickly than the SUV loses it. And in fact, if the SUV loses 10 miles an hour, the VW is going to gain 1, 2, 3, 4 units. Those are 10-mile-an-hour units. So the slope is just 1 to 4, but a negative slope. So the VW, after the SUV has gotten 10 miles an hour slower, this poor VW has been sent 40 miles an hour faster. And just thinking about it that way is kind of a quasi-proof of the axiom we're talking about. But it's not really a proof, because you really haven't said what mass is yet, and you never will in a classical class. That's the quantum mechanics. Okay? So we're sitting here using stuff that is derivable by quantum mechanics approximately. And all I need to do is take my ruler and connect those two. So when we do this later on for other experiments, the way I'm going to do it is say, okay, we need a certain slope. So I'm going to say 1 out, 1, 2, 3, 4 up. and then again, one negative, and then positive, 1, 2, 3, 4. So there's another point right there. Okay? And the ruler should have those 2 points on it, and then you're good to go, right? So the collision, whatever it is, a crunch or a kabong, is going to be, and I'll put the sound effects there, ka-bong. Okay? Now, I don't know where this thing's going to stop, really. That's the question we've got to answer here. And also we have to ask the question, what are the meanings of the values that are down below here? But we'll worry about that later on. In any case, you should have a line on the graph paper that's just this one. Okay? So then the question is, where is the final? We know where the initial point is, but where is the final? Well, let's do the crunch collision first. Remember, the crunch collision is the one where they stick together, right? So here's the logic. The logic is they're stuck together. That should tell us where this line stops. In the middle, so to speak, right? That's what this red line is. So this is going to be called our center of momentum line. So we're done with the first part of this problem. We've solved it already. This is the crunch point right here. Now it's also an important point for all sorts of things that we'll talk about, mainly the balancing of momentum. And in fact, if you're an engineer, you'd put a little one of these circles with a cross in it at that point. So this is the COM line, and it will be for all the collisions that we do with these one-dimensional case here. So this is a momentum line, or the COM line, that will take all sorts of calculations there. So this is the crunch point. This is where you make a single mass going at each of the same speed. That's what the 45-degree line signifies. Okay? Now, the next step on this is to figure out, this is the question that's being asked here, is during a collision there's this line that traverses very quickly after the crunch. When is that? What is the solution to this equation for the upper end there? That's the final right there. Okay? So both of them end up going 50 miles an hour if you do the crunch. That's the end of the collision right there. Okay? But what if they bong off of each other? The kabong, the perfectly elastic collision. What about that one? And what's cool about that one is you get out your compass and draw an arc up to the answer. And so this is what we really have to discuss, because both the mechanics of the perfectly elastic collision and the one that's perfectly inelastic are on the same diagram. Okay? So, I pull out my compass right here. It's a little clanky thing. It's made out of wood. Not too many things made out of wood anymore these days for technical use. And I would really not need to draw the whole circle for this, but I'll do it anyway, since we can use it for other things. And the question is, how close to the correct answer can you get? And I did pretty well there with that one. Okay, and I go ahead and extend that a little bit, just with dots, just to make things more or less complete. And that's all the geometry we need to do today. It's a very simple thing we're talking about here. But here we have an answer that tells us that the Volkswagen is going to be thrown to 90 miles an hour. That's pretty pretty amazing, right? He's going 10, and all of a sudden he's going 90. Ooh, that would hurt. It's not survivable. This might be survivable. And that's why cars are made to crumble. So we're going to be talking about all that. And you'll notice we haven't mentioned energy. That's coming. Okay, that's going to be the main part of the lecture. Let's figure out what energy is. Okay? But this is all there is to the geometry underlies that discussion. So that's where I'm going to pause, make sure there are no questions about this. Yes?
So the reason we drew this completely opposite, like in a circle like that, was that they should exchange velocity, so they would lie on the opposite point, or is there a reason like we're trying to...
Yes, thank you for that question. Might as well say the answer to that as best I can right now. Here, they come together, right? Now, it could be a crunch or a kabong. If it's a kabong, I made a lot of potential energy. And if this is a perfectly elastic collision, I get all the back as they separate.
So we can basically make a smaller circle and then track the velocities again. Yeah.
If we lose some energy, you're going to be making smaller curves. But the other curve that we need here is the ellipse.
Yeah.
We're going to be making a smaller ellipse. That's a quadratic thing, and that's most of the lecture about quadratic stuff, quadratic tensor forms, things like that. We're going to use the kind of mathematics you use for quantum mechanics, because it's what we're going to use to analyze many collisions here. Okay, so that's yes, TC.
Didn't you? I recall at one point where you considered playing it time backwards, where you would interchange the final and initial.
Right, and what TC is mentioning is the time symmetry that we're going to demand of any collision that we call perfectly elastic. Now we give it a name kabong, it means a sound came out, so that wasn't perfect elastic because I got some sound out of that, right? But then you're talking about really tiny amounts of energy compared to these crunching pieces of metal, right? If it's really an elastic collision like you get in quantum mechanics, you don't lose anything, you don't get detected. Okay, anything else that you can think of might be germane at this point? So here are the numbers. Start at 1060, end up way up here at 4090. Okay? So you might as well put the coordinates on these things. This was horizontal 10. I'm sorry. Horizontal 60. I was looking at it like Minkowski does. This is a Newtonian, more of a Newtonian graph. And 10, okay, is the vertical. Up here, the vertical is 90 for the poor old VW. And 40, the SUV is only slowed down, only, what are we talking about? That's also quite maybe not survivable. Changing your speed from 60 to 40 really fast can be very damaging. Okay, but the VW is the one that's really taking it. Okay? All right, now, there's a couple of things about this, and I'm going to take this diagram here very seriously. And in fact, what we're going to do is draw a funny kind of vector that I'm surprised isn't here in quantum mechanics, in classical mechanics courses more often. First of all, your ruler from origin to draw a vector to the first point, the initial point. Okay? And we usually use the color green for that. I'm going to use a bright green because that's the only way you can see it on this board. So I'll put my magnetic ruler down there enough so that I make a decent vector coming out of here. And I'll put a little arrowhead on it, like you do in the thing. And this will be the vector V in. That's the vector 60, 10. Okay? And then you already have a line for the COM here. So put a little arrowhead on that one, just to, be kosher. Okay, and that one is the vector we call VCOM. And then the final, if we make it to the final, and that requires some doing, and I'm going to use a kind of, I had some brownish stuff here, but I don't know where it went. If you'll excuse me a change in color, I'm going to make this one sort of a violet color here. So this vector right here is the other vector in the thing that's on the slide screen right now. So I put some arrows on that one too. And this one I'm going to call VFin, finish, final, F-I-N. Okay? So those are the three actors in this collision. Whatever it is, it's got to end up somewhere, typically in this region. Now there's some really strange collisions we're going to talk about later that end up other places, but let's just deal with this one first. Now what we've got here is the algebra that goes with this geometry. That is that the total mass, that's, we're talking about 4 plus 1, 4 tons plus 1 ton, of 5, total mass of 5 tons, times the velocity at the center of momentum. That's what would happen if this was a current. We'd be right there and stay there. Is equal to, and the axiom 1 is that either one of these combinations of mv is the same numerical value for the momentum. So mv in vw, m2, I'm sorry, m2 is the vw, the SUV is m1. Okay, so here's 5 times the velocity of the SUV to start with. And then here's the VW at the initial point. Okay, he's going 10, this guy's going 60. Then here's this velocity here, they're both 50. And then here's the final one where this SUV is only slowed down to 40, but this thing has been thrown to 90. And of course, there's the equation that really talks about the balance point. M total VCOM. All right, so 3 different ways to write axiom 1. Now we're going to do some fancy ways to write axiom 1 to get us going with the mathematics of matrices and tensors that we're going to use so much in all your courses, but particularly this one. Okay. And anyway, this is where we start with, and that is the VCOM is a weighted average of either the initial velocity 1 and 2, or the crunch velocity 1 and 2, or the elastic final velocity 1 and 2. Or pick any point on this line here and put it in and take the weighted average. You're always going to get VCOM, which is 50. Okay, so the number 50 is equal to all 3 of these things. So we're just dividing axiom 1 by the total mass. Does that make sense? Okay. Makes geometrical sense, but also makes algebraic sense. And that's what we're going to try to set up in some algebra here. So this VCOM is a M1, M2 weighted, literally a weighted average, where the weight of these two objects, multiplying their respective velocities, it's 50 for every point on the momentum line, on what we I'll call this. So we might as well name that. When I say momentum line, let me get over on the side here and write momentum line on that because we use it so much in the text. So that line with slope of -4 going through the initial and final points. Every point on that has this particular weighted average of the velocities of that point. Okay, so that's you know, something to think about. It's another way to say axiom 1. Just going through and looking at all the different ways we say axiom 1 about conservation of momentum. Now, when we do this vector notation, it helps to go ahead and use the mathematics of quantum mechanics, Dirac's notation. At first I do the old Gibbs notation and write a little column vector here, V fin, VCOM, and VN, okay? This I'm going to designate by simply writing a ket, that's half a bracket, and putting the letters IN for N, initial, inside there. So this is what, if you're taking quantum mechanics, almost everybody uses this notation now. It was a few years ago, it was only a very special thing. But now it's become pretty well. So let's use it here. Okay, so these are the old-fashioned Gibbs notation for Josiah Willard Gibbs, an American physicist, went over to Europe to learn physics around the 1900s. Now, you may be used to be giving coordinates like x and y as a bra. And when you do that, if you use Gibbs notation, you have to point the arrow this way. See the little arrow up there? So the bra points that way. Okay, this is making a connection now between stuff you do in QM and stuff you're going to do here. This is very classical at first. Okay, does that make sense? Bookkeeping is the major part of the mathematics of physics, right? You find different ways to do the bookkeeping. And that way you can read more of the papers, because everybody sort of does have a different style of bookkeeping. So, what we're interested in is the dot product, dfin.dn, for example. Okay? So here's the bra vfin. I'm going to do a dot product with the ket vn. Okay? This is the Dirac notation for that, fin.in. Okay, and of course it's just a sum of the products 40-60, 90-10. It's a matrix product basically of two of the minimal matrices, a column and a row. Row vector is the bra. Column vector is the ket. Okay, so this is a notation that we'll use a lot. We'll also use a Gibbs notation, perhaps more than the Dirac notation. Now you should be aware that you can make a matrix out of these things. This is called the outer or Kronecker product of, now you put the ket here and the bra here, the arrows are pointing at each other. When they're back to back, then the back ends of them, those are the things that can interact with an operator or the other vector. That's the dot product. That's the scalar product. This is the tensor product of the two vectors. A little circle cross here is the most common notation after a mathematician named Kronecker. So here sits this. So now you get 60 times 40, you just write it down, you know, do any summing with it. Then you do 60 times 90, that's right here, and so forth. 10 times 40, that goes here, and 10 times 90, that goes here. So you get a big matrix with hundreds and thousands of things in it. And we'll kind of make a little bit of use of that, but I just want to show this so that you see the complete repertoire of things that come from playing with two-dimensional entities. This ket and that bra. Okay? So, how many people here are already comfortable with Dirac notation? One, Bill, you. Good. Okay, so I'll get going here. The thing I want to do after the idealization, I want to point out things that are pretty obvious here. And this is what makes us have the ability to analyze anything, is we ignore a lot. No rolling friction, no air resistance, no going off the road. This is all one-dimensional stuff here. Cars are constrained, so it's kind of like an air track system, okay? And when we break down that, when we consider other degrees of freedom like x, y, and z, not just along one axis, well, you need more algebra, as you see, and more geometry, more complicated geometry. So really, both of those cars have 3 translational degrees of freedom. So now we're up to 6. We're up to 6 dimensions just with this collision problem here. If it were happening, say, in space, where they could go all 3 directions for each. Okay? And then, of course, they're not just particles, these are cars, so they can rotate. There are 3 dimensions of rotation. Air pilots call yaw, pitch, and roll. We call these Euler angles, and that's what this machine here is an Euler angle machine to keep track of those things, which we'll be doing when we get to talk about rotations in 3 dimensions. And also we use it to catalog spinner mechanics. Okay, so there's all kinds of things waiting here just in this introductory unit. Okay, so his got 3 rotations, this guy's got 3, there's another 6 rotational, so we've got 12 degrees of freedom here just with 2 cars, or 2 spacecraft, right? We're not done yet, right? This is, these things vibrate, okay? It's a molecule, it'll have all kinds of normal modes, it's another molecule, same thing, or even if it's a nucleus, it's got normal modes and states. Well, there's no end to what can happen there. So we're talking about 12 rigid body degrees of freedom plus. Now, in units 3 through 8, we're going to be taking up situations which have these higher number of degrees of freedom. So 3n minus 6, where n is the number of particles, and then a molecule has that many degrees. You can see right away ruler and compass geometry is probably going to be on the losing end of the logic as we go to those higher dimensions. But always, no matter how many dimensions there are, you always grab 2 of them, maybe a 3rd one, and play games with your mind. Okay? So that's important. People don't realize that. That's really powerful to know that. So we're going to go back to 2 right now to get started with the ideas that are behind all of this. Now, what's the geometry of a Galilean translation? Okay, now here's Mr. Galilean. Always looks grumpy. I've never really hard time finding a photograph of him smiling. But it turns out that his Galilean rules really break down for relativity. However, I found a way, and it's really important, and that's what this stuff is all about. If you use something called rapidity, you get to use his rules of addition for that. And that's Lorentz group behavior that most people don't know about very well. But here is very simple. The idea is if you increase your velocity by 50 miles an hour, or 0.5 miles an hour, okay, which I'm going to do right now, I'm going to go 0.5 miles an hour faster, and I just noticed that all you guys are going 0.5 miles an hour relative to me. Right? There you are. I told you. I'm passing you. Okay? So that's the idea, is that according to Galileo, the rest of the world appears 50 miles per hour slowing in that direction. That's sort of a heavy statement of the Galilean rule for velocity addition. Now we have a velocity graph here, so how do you do a Galilean translation? You add or subtract the same velocity from all the points that you have. That means you slide down the 45-degree line. So you start with a collision that's here, and you can go up here, and there'd be your new points. Or you can come down here, and this is a really interesting one right here. That's the center of momentum, where it's really easy to calculate, and also easy with low amounts of dollars to get energy out of particles. head-on collisions, okay? Or you can go down here and have this thing looking very negative. All of these are possible points of what we've just done. Okay, here's a whole bunch of them. Some are special. Here's one where the VW, that's this axis, wasn't going anywhere. He's actually standing still in this frame. And then here's one where the SUV ends up going nowhere at the end of the collision. Okay, and so forth, you see. There are a whole bunch of very special places, as well as all of the general ones in between. Okay? So 5 of these have 0 for a velocity coordinate. But all the rest of them pretty much don't. But this one is very special. That's the one that's, you might call a time symmetry. This guy, very special. Okay? Now, this is the one where you do a time reversal, that is, you change velocity sign. And it just goes from the initial to final, or final to initial. They switch. But the other ones you see, when I do a time translation, these two switch. So you switch this collision into this collision, while you're switching that particular one into that one. So time reversal here is a reflection, but it can be in lots of different directions. Okay. So time reversal means flip time to minus time. That's run the movie backwards. That means you flip velocity to minus v. Basically everything goes backwards. It's like running the movie backwards. That's the time reversal, right? Okay, so that's an important point about this thing. So here we are. As I say, this is just one velocity frame that has the time reversal behavior. Okay, now let's do a little bit of the vector algebra that's involved in these things. First of all, Gibbs notation for a dot product. And we are talking about momentum, and it's total momentum. And remember, the dimensions that we're talking about here belong to different particles. There's the SUV particle, there's the VW particle, right? Those are the 2 dimensions that we're talking about. This is a weird kind of vector analysis. Like you're used to one X, Y, and Z, and maybe T if you're doing relativity, right? This is just different particles. 1 dimension for each. Okay? But we're going to use the same sort of bookkeeping for that. Okay, so when I say I did the matrix here times this one, I get a sum here and here if B and C are not 0. Now we're going to mostly work with things that have a mass here and another mass here, M1 and M2, and nothing here, because that's an ordinary space. If you guys do any solid state physics, you know that the mass is a tensor in that business, in solid state things. Okay? So we're going to be doing something that lets you do that sort of work as well. Everything that we do does not have to have a diagonal matrix, but here we do. Okay? So we're going to do the vector algebra of the collisions. We're going to do just to see if Dirac notation is simpler. Well, yes and no. Okay. When I say x in, I mean the x component of n. Y in, I mean y component of n. That's fine. But this guy right here, a, b, they need the Dirac notation too. You see, and as soon as you do that, then Dirac notation gets to be a little bit more complicated. You have to do more writing onto this than you do for this.
So I have a question on B and C. Are those, if there was a collision and the masses were to transfer, that one object became bigger and smaller, would those like describe that transition?
If you were to have a collision of some sort of polaron that had a non-diagonal mass matrix with another one, okay, there are all sorts of things that can happen. Okay, I mean, it's crazy because your effective mass depends on what direction you're going too, right? And So it's, you know, it's not an easy problem at all like this one. But there are ways you can make it easier, I think, but that's getting a little ahead of us here. Is that any more I can add to that? At this point, it probably wouldn't be worth much. Okay, so you put this all together here, and you see this. Wow, that Dirac notation is probably not the one we want to use all the time. But in any case, this is the situation. We're going to write this vector equation. That's what's going to help. We're going to use the Gibbs notation primarily here. So we're going to have an M matrix, but that M matrix is not anything but 0 here. Okay. So when we built these equations that we lined up, we're going to rewrite those things using these matrices, you see. So here's the momentum number 1. That's our SUV, the bottom axis here. Here's momentum number 2. That's the VW axis. Okay? We don't have anything here. But as I say, all throughout this course, we're going to be developing a Lagrangian mechanics that lets you have non-zero here and non-zero there. However, you're really going to get in trouble if you make them unequal. That is going to be really squirrely. Okay? So you won't find that at first when you do these solid state things that I was talking about. I say at first because you can always turn on magnetism and that makes them not be Hermitian conjugate. Anyway, here's that equation all again. Okay, here's the initial. Here's the final. Here's the one that we use in the middle. That's the COM. Okay, and then here's just the total mass times the velocity. That's the scalar number. Okay, I want to turn these into vector equations. I just want to rewrite them as that. Okay, I went backwards there a little bit. Okay, the product of the total momentum, P total as a number, okay, times VCOM as a number is going to be this, or this, or this, or this. So this is just some really sort of fancy ways of writing Axiom 1, okay, for the momentum constant, equal constant, this constant right here. Okay? So, I want to do the numerical details of this. Now, your first problem, which is due next Tuesday, is to do this, but for very small speeds, parking lot speeds. So we're going to have an elastic collision for the most part in that problem. And here's what you're going to be writing, or calculating, writing down. Also, drawing the geometry to go with it. So what we see here, first of all, is the VNs here, the mass matrix of 4 tons and 1 ton is here. And then the VCOM, now what's cool about the VCOM is they're always equal, right? It's one crunched metal, right? It's this point right here, 50-50, okay? So I can turn this into a scalar product, you see, with 50-50 right here. Then I have this here. Then 50-50 right here, and a final right there. So this, called quadratic form, quadratic in the sense that 2 vectors go in, get acted on by a matrix that gives you some number. So we'll be seeing quadratic forms for the metric of a kinetic Hamiltonian or Lagrangian, okay, in this course. But quadratic forms are called expectation values often in matrix analysis of UN. So get used to them. They're all over the place. Okay, so that is what we're working. Now what we're talking about here is M total of 1 plus 4, that's 5, times 50 times 50. So we're talking about 12,500 is the number that's the constant here for this very funny way of writing Axiom 1. So axiom 1 is now a constant, not about momentum, it's a product of momentum and velocity. That has a name, it's called action. And we're going to be playing a lot with action. And that's the sort of unknown quantity of classical mechanics. And if they'd really played it out, they would have discovered quantum mechanics a lot earlier. So anyway, here's this thing being written together, and this one too. And they're all different ways of adding up 12,500. 50 times 5 times 50. Okay, so these are things. Now, already we're into chapter 2 and headed for chapter 3 of this textbook. So, as I say, we're covering a lot on this first day. Okay? All right. Now, what I want to do is derive, not just state, not make an axiom out of this. I want the conservation of energy to be a theorem. Okay? As best you can do. All right? And then the geometry of that is the geometry of the ellipse, which is very interesting. So let's see how that comes about from playing with these matrix quadratic forms. Okay? And what this bookkeeping way lets you do is each time you do an algebraic manipulation of some type, you go ahead and work it out just to see if it's adding up. If you're getting the same number out of this thing here as you are out of this thing here with 6010 instead of 4090. Okay? So you get to check yourself. So basically what we have is shall we say, the quadratic form exposed. Now, the other half axiom, the one that you don't call an axiom, is the time reversal axiom. That is, if I assume that these collisions are perfectly elastic, and I'll go ahead and advance these slides here to the point where we actually had that happen. That's the point right there, where we crunch and then uncrunch, which we call the cabal. Okay? So when you have that situation, you have a geometry that's very symmetric. That is, the sum of these two vectors, first of all, worth noting, and I'm going to go ahead and add another line, have it add another line to your graph, but I'm going to take this vector here and put it over here. Now, let's learn how to do that, because we're going to have to do this for other things. Using your compass, you can very quickly do that. At least you can get a pretty good approximation. What you do is you set your compass, say for the bigger velocity, and mine is just stretched out almost to its limit, okay? And you strike an arc from this point to figure out where, I'm doing a little sloppy job there, and then you do the same thing with this vector right here. You set the compass with the number 1 vector, the initial vector here, and then you strike an arc on your graph paper using it. Oops, I let it change its diameter. I've got to tighten this thing down so that it won't move, and make sure that it is the right value. And then put it on this one and strike an arc, and where it goes, no one knows. Oh, well, that's pretty good. That's the sum of these vectors, okay? So what you have is a parallelogram. That's very important. Force, you have forced triangles and forced parallelograms, right? In initial, I'm not going to use that old thing anymore. I should use the modern one right here. to the point where those crossed, and then you have the thing that's shown on the slide. You have the vector sum indicated. And what you're seeing, of course, is half of that vector sum is the COM point. So this is what we're working with right there. Okay? And we'll be drawing many of those diagrams as we explore multiple collisions and various things that have to do with that. But this is axiom 2. The idea that this point right here is half the sum of the final and the initial. And that won't be true if I only make it to here or to here. Then the final plus the initial is going to be down in here someplace, not right here. So to answer your original question when we asked about, okay, I crunch together, and then if time reversal is true, I uncrunch perfectly. Otherwise I fall short, right? And if I fall short, this is not true. This axiom 2 is not true. So this is the time symmetry axiom. And most people don't, all of your quantum mechanics at first demands time symmetry. Otherwise it's completely screwed. The actual waves don't never have problems with this. They kabong all the time. Perfectly, without making a sound. Okay? So, what we can do is go ahead here and rewrite VCOM, this one, and this one, as the sum of Vfin and Vn. Half sum. Okay? That's what's going on here. All right? Then we can pull it apart. Okay? I can write this thing as a kind of weird quadratic form where there's two different vectors, and then one was just two of the initial vectors. That quadratic form is one we're really interested in. That's the energy thing. But this one is interesting too. This is a lopsided one where the fin is on this side and the n is on this side. Here the fin comes first on the left, and the Vn is on the right. That one's just the opposite. But then these two guys, right there, those are your kinetic energies. We're going to try to get those out of this equation. Okay. The way to do that is subtract this thing. But subtracting this thing maybe doesn't kill that thing. Well, that's what we have to worry about. These are now the numerical details of this, where we put all of the things here. And the first order of business is if that M matrix is symmetric, and I would say Hermitian conjugate, we have no complex numbers here yet, comes later. But what we find is if you have a symmetric matrix, these two have to be equal. Well, it's trivial here, okay, because I've got a 4 and a 1 here multiplying the square of the product of 40 and 60, and then the 1 multiplying the 90 and 10. That's going to be the same as turning the products around, putting 60 on this side and 40 on that side. That's the same as 40 times 60, or 60 times 40. So you end up here with something that's 10,500 for both of them. So when I subtract this thing, this thing from this equation, I will also be subtracting this completely. And I'll be left with my conservation of kinetic energy. Those two terms there will just be equal to each other. Okay, so that's what's going on here. Take that fin in term, subtract it, that gives you conservation of kinetic energy. That is a theorem. But it demands time reversal symmetry. Okay, so that's cool. Okay. Now you check the numbers, of course, because it's pretty easy to screw up while you're doing this algebra. Okay? A lot of numbers you put in places, and if you put them in the wrong places, look out. Okay? So to save you time, I say do the bookkeeping step by step so that you check yourself along the way. And also look at the geometry that you get. I actually want you to do a plot in that problem, just like the plot that we have already finished here, but I want to point out parts of it that are key to this. So here's the kinetic energy for this guy right here. Here's the kinetic energy for that guy. According to what we've done, it should be equal. Bingo, 7,250 for each. Okay? Is all making sense? More or less? And that's why I gave you a problem, because the only way to really get this to be in your head is you've got to rub your nose in it. Okay? You've got to play with it. Okay? Just to get a feeling for the simplest of quadratic forms and how they play a role for such a simple thing, just two particles bouncing off each other. Well, what does it look like graphically? Now, I should point out all of these things in the lecture, and this is why it's good to look at this thing on the web, because if you just click on one of these things, you get an animation that shows something interesting or beautiful. I mean, it's pretty to see this stuff happen, but I'll leave you for that. Do that on your own. For the most part, we'll come back. So anyway, here are the three vectors that we were talking about. And here is the ellipse that goes with this thing that we claimed was 7,250. 1/2 mv squared of each of the m1 being the SUV and the m2 being the VW, the second axis of that graph. Okay? And you break that down. We're going to do this several times in this course with these quadratic forms. Break them down so that you're equal to 1. Divide through by whatever the total is. And write the thing here as a square root squared, because then it's an equation for an ellipse in the diagonal axes, in the eigenaxes, if you will, of this quadratic form matrix. Okay, so this has an algebraic form that's very easy to calculate. So this is what you need in order to do the construction of the ellipse, if you're going to use the method that's in Chapter 3. And that's mentioned in the problem, to go to the end of Chapter 3 and see how you construct very easily, very beautifully, points of the ellipse, this particular ellipse. But look at what it's doing. You see this? See how it bows out there from the momentum line? You'll have a more spectacular problem that I've given you. And this one is barely visible there. Okay, and that's because these guys were going in the same direction. What I'm asking you to do first is to run them into each other. Okay, at the same, more or less the same speeds. Okay, so you got to know 60.21 and 120.42 as the values that you would plot on the graph. And the graph paper I've given you will let you do that fairly precisely. Now this is what's coming up here. We're almost at the end of the lecture today. But what's coming up here is the fact that after you've done one of these collisions, if you put something around this thing and think of it as air cars, and forget about the poor SUV and the poor VW who probably died in these collisions, here it's just two balls, and we don't care what happens to them. They just go kabong, kabong, and they do some rather remarkable stuff. And that's what we're going to talk about in the next lecture on Thursday. Is all of the weird stuff that you can make. So you're going to have a way to really use those matrices, and then you can make a pretty good theory of what the things do. This is just a picture of them going many times here. But they always end up on the quadratic form after they've done their collision. So that's what the ellipse really means. It's taking all possible states, given the in and the fin, whatever that is that you gave it. It defined an ellipse right away. And then forever and ever, if there's no loss and it's time reversible, you're going to be ending up on the ellipse. And that's cool to see. Okay, now, here's just some other comments about the transpose symmetry, allowing us to take that lopsided term and put it on the other side. And then there's an ellipse I'm going to ask you to draw that corresponds to the crunch, the kinetic energy ellipse for the crunch. Not terribly useful. If things are going to crunch, you're going to lose energy, just keep losing it and end up at zero finally. But it's worth taking a look at that and comparing the energy that you get here to the energy that you started with. How much, first it's potential energy, if this is reversible, how much potential energy is there in the these colliding, whatever they are, that are pushing on the springs that are going to spring them back and return them to the point on the ellipse where the kinetic energy is exactly equal to what you started with, not something less, which is along these line right here. You see that? So that's an important part of this. And again, the numerical values of all of these things are being displayed here. And that's what we call potential. And it turns out to be 1,000. And I'm going to add, that's what I want you to do in the problem, is make sure you get that number. And then notice that that number appears no matter what frame you do. If you do a Galilean transformation and come down to here, then you just have the collision that they do at the Hadron facility, where they just work with head-ons that have time reversal symmetry built in. And that's where you make the smallest ellipse. And guess what the kinetic energy of that ellipse is? It's exactly the kinetic energy that we crunched right here. It's a difference between what you get when you're together to what you were when you started and finished, if you had an elastic collision up here. Having one down here makes that ellipse. And then these lines should be tangent to that ellipse. So there's all this beautiful geometry hiding in just two particles, right? Okay, any question? We have a little bit of leftover time here. I'm trying to, finish it on time, so you've got to pick up some kids, right?
I have to leave till 2, so.
Yeah, so we can open the floor here to this. But these are things that, this is in the textbook actually, in chapter 3, a picture of that, and then a picture of this, which is the smallest ellipse you can get if you don't lose energy just by doing a change of frame. Now this points out, as usual in physics, these opposite extremes are easier to analyze. The real world in between, right? Ending up somewhere on here, I call it a kahwump. Statistical physics takes over here, okay? But if somebody tells you how much energy your kahwump was, you draw the same sort of thing, you see. Now it becomes interesting, what happens, is it possible to end up on the lower portion of this thing? And that's cool. You should think about that. Because in quantum mechanical systems, that's what's going to happen all the time. Waves have to go through each other. That's what's going on there. Okay? Now here's the construction I told you about. Okay? You know B, you know A for an ellipse. Major radius, minor radius, say. But in our case, A and B just means, A means horizontal radius, B means vertical radius. We got an ellipse on its end, so the major one is going to be the B. So don't let major minor screw you up there. This one is more like the classic ellipse, okay? all you do is draw a line from the center to the outside. And then you let the graph paper tell you where the intersection to the inner circle collides with the downcoming intersection for the larger circle. Bingo, you got a point on the ellipse. Okay? So you can play the game of, I would like to find I just draw a line here and figure out where that thing is on it. I just find out where it intersects and make the little shoes. I call this the heel and the sole of the shoe, and that's that blinking thing happening again. There's the sole of a shoe, there's the back of a heel, right? A little triangular shoe, right? And here I just sort of lay them on top of each other to make successive points, but any point on there can be done. And later on we're going to use this. This is a harmonic oscillator trajectory for isotropic oscillator. It's a really cool way to calculate the trajectories of that. And here's just what's going on with sines and cosines. So make sure you take a look at that. And I think it'll be easy to do these problems by next Tuesday. Okay. And this is a graph paper that we use today, but the graph paper that's good for the problem is hanging on the back there. You can get it online too if you lose it. Okay.
Incidentally, your textbook is also present online in digital form. So if you're away,
yeah, make sure you
on the bus.
It is just a textbook. It doesn't have you can't click on it for the various funny things that happen here. Like, let's go back here a ways.
So we also include the lecture notes.
Yeah.
And
see
here
this
within a day
thing
we'll have
right
the
here.
video.
Is here comes the 4-ton SUV. Here's the 1-ton, well, it's grams because we're really talking about little ball bearings. Okay, and there's the velocity plot there. There's the bang. It was really quick, right? Okay, so now we've got that part of the curve, right? But this doesn't stop. Well, it does stop because, when I use it just to talk about things, you do have to click the resume, and then it will go forever, making, there was the bounce off of the top. There's another kabong up to here, right? And then come back down here, okay? Bang, right? You see what's happening? So that's, fun to play with. And of course you can check yourself on your ellipses and things with this, because if you do the controls here, they're a little bit squirrely for setting the masses and the velocities, but it should be fairly self-explanatory. Have any questions? We both have emails, and particularly about programs, TC is the one who turned all of my old programs from Faceit and Macintosh so that you can work on any browser, and that involves Java and HTML and, well, it's HTML5, right?
5.
Yeah, but it's grown to a monster already. So I think what you're noticing here is there is some symmetry to having a mass ratio of 4, and you make and that's, we have to discuss that later on. And in fact, there are a lot of things about the symmetries that these trajectories make that I don't understand. And if you can add some light to that, we do American Journal of Physics article on that, which would be nice, to play with. You have lots of time, right? So there is a possibility anyway for doing that. All of this stuff came out of me teaching a course at Southern California when the Super Bowl first came out. So we'll be talking about that tomorrow too. At that time I hadn't thought of this yet. So that makes it a lot easier to understand how the collisions play with each other. But this is a Lagrangian curve right here, and it represents a bowl, it's a topography line for a bowl coming out of the screen, energy this way. And you're talking about 1/2 mv1 squared and then 2v2 squared, right? So it makes an elliptical paraboloid. That's the Lagrangian of this problem. And Lagrangian is defined as the function of velocity that gives you energy. The opposite sort of that is the Hamiltonian, which is writing them in terms of momentum. And then there's something in between that we're going to talk about in the introductory chapter 8 and 12, and I don't have a name for it, so I call it Lestrange. Lestrange. No name at all, right? It's where the circle, it makes a circle. The Hamiltonian makes an ellipse this way. You can draw all three of these on this program. If you want to explore ahead, that's available also. Okay, so I'm throwing stuff at you at the rate of fire hose water, right? But you now have virtually all the clues to doing that particular problem set. Yeah, Brad.
This, if I'm remembering, the slope is a ratio of masses. Is that correct?
Minus m1 over m2.
Minus m1 over m2. Okay, so if let's say you have one point on the zigzag trajectory is a rational number, and the slope is rational. Is every other point a rational number? A rational pair?
If you were to say, here, in this particular one, we started here.
Say that's rational.
Yeah.
A rational pair.
And then you're asking, at the end of that, do I get a rational number?
Yeah.
You
Rational
stick
pair.
that into our algebraic equation, and it's just summing and squaring, right?
Yeah.
So it would have to be, right?
So,
In other words,
I'd
look
have to
at the,
work it out, but I think
yeah.
it is. Yeah.
I think that's definitely the case. That you,
And then the other question is there any...
That's a good point. I think, now that I think about it, I would like to explore these things by having a program that doesn't have to go through the Rungu-Kutta that this one does,
Right.
actually following the trajectory, everything. Let it do the algebra. At this point, bam, 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 you could
Yes.
do 1,000,000 trajectories in a second, right?
Well, you could just
That's out
iterate. You could just
The
iterate the
matrix
solutions
iterator
on
is out there.
on the boundary.
Mm-hmm.
But then, the other question is, if you let this thing go, well, okay, between, what does the angular function look like for the hits on the boundary?
That's really screwy sometimes.
Is it?
But if you make this guy real long,
Yeah.
and then just let her roll around and then come back and roll again,
Yeah.
okay? The first time around, it just makes sines and cosines of a fixed angle. That angle, the Lestrangian angle,
Yeah.
is always the same.
Yes.
I don't know if you remembered that.
Well, I don't, it's been a while, but this
Yeah.
stuff is reminding me of the cryptographic systems I've been looking at recently, because...
If you could make a connection from this really elementary stuff to that would be great.
Well, here, the weird thing is they put it all over a finite field, so, if you iterate,
Mhm.
if you get the points of the ellipse in a finite field and you iterate over the finite field, maybe you can get something.
And you use the simple algebraic equations that are producing this,
Yeah,
you would stay in the field, right?
yes. Well,
If it was a field of rational numbers, right, is what you'd be saying?
yeah, basically.
You would stay in it.
Well, you go from a field of rational numbers to a finite field. And then you're doing
Yeah.
modulus arithmetic.
Sometimes you do, and sometimes you don't. And I don't know when you do exactly and when you don't.
That part is kind of confusing.
That's why I want the one that takes 1,000,000 steps a second. Right. This is too slow.
We should look into that maybe.
But the matrix iterator is out there. You can go ahead and convert it to whatever.
Yeah, we can,
Whatever you prefer.
the tricky thing there will be setting initial conditions and initial finals, right? Yeah,
Dialog box.
here we just let it go until it you know, cows
this
come
also-
home. But if you could fix it so that it would stop at a certain point.
Search them out.
Yeah,
This
search
also
point.
has to do with the so-called QRT map. Have you ever heard of that?
No.
If you
Quotient ratio.
no,
What
it's somebody's name.
transpose.
It's somebody's name.
Oh, that's a bunch of
But
people's names.
let's say you have what's called a biquadratic function.